Hi everyone, this is pre-class video on module 2 on course Power System Analysis 1. The module name is Symmetrical Fault Analysis. In this video I will be explaining the concept of transients on a transmission line due to short circuit. Myself Dr. M.J. Chandrasekhar, Associate Professor, Department of EEE, SAB Institute of Technology. The topics under this module 2 on symmetrical fault analysis are introduction, transients on transmission line, short circuit of a synchronous machine, short circuit on a loaded synchronous machine, illustrative examples, selection of circuit breaker. So, in this class I told you I will be explaining the transients on a transmission line due to short circuit. In the modern interconnected power system, so the AV currents are flowing due to the fault that must be interrupted before the steady state conditions are established. For selecting the circuit breaker, we must therefore determine the initial current that flows on occurrence of the short circuit and also the current in the transient that flows at the time of circuit interruption. It is observed that the shunt capacitance will be very small compared to the inductance, hence the line can be represented by a lumped RL network in series with the internal voltage. The faults will disturb the normal flow of current. The disturbances are caused due to the short circuits or open conductors. The faults are broadly classified into symmetrical faults and unsymmetrical faults. What are symmetrical faults? Symmetrical faults are the faults due to which the fault current is same in all the three phases, and unsymmetrical faults are the faults occur due to the uneven distribution of voltage and current in each of the phase due to the disturbance. So, now let us consider the topic of this video, that is transients on transmission lines. So, the line we assume that it is spread from a constant voltage source. So, it is assumed that the short circuit takes place when the line is unloaded, and here the line capacitance are very small, its effect is neglected and the line can be represented by RL network. So, here compared to RL, the line capacitance across this, so that is neglected. The applied voltage, the constant voltage source, it is supplied, the line is supplied, and the constant voltage source is of the AC, then V is equal to Vm sin omega t plus alpha. There here Vm is nothing but the RMS, Vm is root 2 into V, V is the RMS value, and Wt is the phase angle of the input voltage, and alpha is the provides the way to control the timing of which the short circuit occurs. So, the steady state current and transient currents will put together will be the I in the event of any disturbance. The current I of t flowing in the circuit after short circuit can be arrived at by applying the differential equations, Laplace transforms and some algebra. See, here we have considered the current equation I of t is equal to Bm by z into sin omega t plus alpha minus theta. It is the steady state current or the symmetrical short circuit current. Here theta is nothing but theta is tan inverse of omega L by R is the power factor angle, and current I of t flowing in the circuit after short circuit can be arrived at by applying the differential equations, I told you, Laplace transforms and some algebra. The angle by which the steady state current lag the voltage, and the impedance here, the impedance is root of R square plus omega L whole square. So, this equation has two parts. One is the steady state value of the current in the circuit, and it is called the symmetrical short circuit. This is I1 of t, that is Vm by z sin omega t plus alpha minus theta, and then the second part, that is I2 of t. I2 of t is the exponential decreasing function of time. This transient component is called the DC offset current. This causes the voltage this causes the total short circuit current to be unsymmetrical till the transient decays. So, this is given by I2 of t Vm by z sin theta minus alpha into e to the power of minus r by L t. So, these two currents put together will be the current flowing in the RL circuit. Now, let us write the plot of V and I versus time. In this wave shape, as you are observing, the waveform of voltage and steady state current under short circuit conditions. So, here the steady state current is shown, and alpha is nothing but the angle, control angle when the short circuit occurs. So, here theta, V and I. So, the angle is alpha. Now, this is the DC offset current, that is the transient state current, then I2 of t. I2 of t, as we know, Vm by z into sin theta minus alpha e to the power of, it is exponentially decaying. After some time it decays, and the club of these I1 and I2 will be the total short circuit current. This is the total circuit current, and this IMM is nothing but maximum momentary current, and this I is nothing but the sum of I1 of t and I2 of t. As you seen, the plot of V steady state current and the transient current and the total current as shown before, it is easily follows that the figure that the maximum momentary short circuit current corresponding to the first week, if decays the transient current in the short circuit, time is neglected. So, maximum momentary current is nothing but Vm by z plus Vm by z into sin theta minus alpha. Since the transmission line resistance is small, theta is almost equal to 90 degree. So, with this I will be ending this video. So, in this video I try to explain how the transients analysis can be done on the transmission line, and it is having a steady state current as well as the transient current. The combination of two will be the short circuit current, and with the help of equations and wave shape we can explain the transients on transmission line due to short circuit. Thank you.